All right, so today let's look at this lab 8, which has to do with sorting. So we're going to solve this problem together. Well, I'll solve it. And then on Monday, we can review for exam 3. And then a week from today, on Wednesday, there is exam 3. All right, that's the schedule. So here's the problem. Exercise 1, sorting. So here's the function signature. It's a function called mySort. It takes a vector v. And the values that are in v are in some random order. And our job is to rearrange those items in v so that they form a non-decreasing sequence, or they're increasing. And then we need to add test code for this as well. So let's start by creating a stub for this function and making sure that our test program is working with the stub. So mySort doesn't return anything. It does what's called an in-place sort. It doesn't make any copy of the vector coming in. See, we accept a reference to a vector. So we're going to operate directly on the vector without making a copy of it. So we create a vector. This one's already in order. And then we'll basically call mySort on v. So this is a good test case right here, actually, is to make sure that the sort routine doesn't alter a vector that's already in sorted order. So after calling sort on v, we'll assert that that v of 0 is 3. We'll just go down the list. We have 1, 2, 3, and 4. So it's 3, 5, 7, 9, and 12. So you just want to make sure that mySort, when it works, it can handle a pre-sorted array, and it doesn't change it. It doesn't change it, right? That looks good. All right, let's create another test. And I'll use this. So we'll create another vector, say u. And we'll just change the order in which we insert these values. There we have an unsorted vector. We'll call mySort. Call mySort on u. And we'll check to see that the values have been rearranged into the correct order. So this should fail. There it is. All right, so we have our test code set up. Let's go ahead and implement this function. So let's think. To sort the values, let's let me take. I'm going to try to show this with some kind of a diagram. So 5, 12, 9, 7, and 3 was weird. Okay, so let's do it like this. We're going to have an index, call it I, and this I is going to pass through the whole vector. Actually, we'll stop at 7. And so what we'll do with I is, wherever I is, we want to make sure that that everything to the left of I is in sorted order. So right now, nothing is to the left of I. And everything to the left of I, including I, is in sorted order. So what we do next is once we set I to the first value, then we're going to use another index j to range across the remaining part of the vector, looking for a value that's bigger, that's smaller than the value at I. When we find a smaller value, which we'll find at 3, in the last slot rather, we'll find 3. We find the smallest value to the right of I, and then we'll swap 3 with 5. So this becomes 3. This becomes 5. And then we advance I. So at this, when we start here, our concern here is everything that's at position 0 and before position 0, which is nothing, should be sorted and sorted with the smallest elements in the vector. So we scan across the rest of the vector to the right of I, finding the smallest item, then swapping it with the value at I, and that gives us this vector here. Now we have everything at position 0 and to the left of 0, which is nothing. Everything at that position is in sorted order using the smallest elements in V. Now we increment I and repeat the process. So j is set to 1 past I. And then we scan across the remaining values until we find the smallest value. Once we find the smallest value, we exchange the values at I and j. So this would be 5, and this would be 12. Now, you'll see that everything here, everything at I and to the left of I is in sorted order and includes the smallest elements from V. Now we increment I and we continue the process. Start with j equaling to 7. Then when we move j to 12, well, we didn't find a smaller value. The smallest value is 7. We exchange the values at I and j. So this should be 7, and this should be 9. And then we advance I. Start the process again with the nested loop that controls j. J is set to the value just past I. We compare the value at I with the value at j, and j can't go any further. So actually j is at the smallest value. And so there's nothing to exchange. So we leave the vector unchanged. And we'd advance I. And we say, wait a minute. There's nothing after I to look for anymore. We're done. So now the vector is in sorted order. Now, one detail that I kind of left out here was how do we label the smallest value that we find to the right of I? I want to also add that there are many different ways of doing this algorithm, and I'm just showing one here. One way to do this algorithm is every time we advance j, we check the value at I and j. If the value at j is less than the value at I, we swap them right there. That's one way to do it. The other way to do it is to let j range from I plus 1 to the end of the vector, keeping track of the smallest value that we find. So we'll need another index for that, say k. And so we delay the swapping function until j reaches the end of the vector. Then we say, well, k is pointing to the smallest one. If the value at k is less than the value at j, we'll swap the values at I and k. So I'm explaining two different choices to you. Which one do you want to go with? Well, first of all, the second choice is more efficient because we're only doing one swap operation at most through each pass of the inner loop. But that second choice, which uses an extra variable k, so it's more confusing to think about. So if we want to sacrifice a little bit of efficiency to make the code perhaps easier to understand, we can go with the first choice, which is to swap the values at I and j each time we find a value at j that's smaller than the value at I. I don't know if that's a lot of talking, so maybe you didn't understand that. What do you want to do, choice 1 or 2?
2.
Huh?
The more efficient one.
Yeah, 2.
More efficient, number 2. Okay, here we go. So we use a variable k to mark the smallest value that we find to the right of I. So I starts at 0. I is less than what?
E dot size.
Strictly less than b dot size, or less than b dot size plus 1, or b dot size minus 1? How far do we let I go?
B dot size minus 1.
Huh?
We'll just strictly list them. Yeah.
This is the one-off problem. You got to think about this, right? Like, when did we decide to quit doing any more work? What was our decision? What happened?
When I gets to the end.
When I gets to the end, what's the index number? What's the
One less than the size.
it's size minus 1. So when I reaches size minus 1, we don't need to do anything more.
Right.
So we quit when I hits size minus 1. So I must be, in order not to quit, I must be strictly less than size minus 1. If I reaches size minus 1, we quit because there's nothing after I to look at. Size minus 1 is the last index. Yeah. See, that's that one-off problem. That you got to spend some extra mental energy to figure that out, right? All right, so we've got I ranging, from 0 to size minus 1 and quitting at size minus 1 without doing anything for size minus 1. Now we need to handle j. What does j start at? When we initialize j, this is an inner loop, by the way. So let's suppose I has just been adjusted, it's just been incremented. What do we start j at? Huh?
1. Because we start j as 1 after I 1.
What's that? 1 past I, right?
Yeah.
So I plus 1. That's where we start j. That's right. So we want to look to the right of J. So J is less than, well, how big does that?
No.
I heard a no. How far does J go? What value should J hit?
12 or 5.
It should hit size minus 1, right? Size minus 1 is the last index, the last valid index. That's what the 12 is. So we want to let it hit size minus 1. We want to carry out the algorithm when J hits size minus 1. But when J goes beyond the end of the vector, when it hits size, then we want to quit. So we'll use J less than V dot size. This will let us quit when J hits V dot size, which is 1 past the end. See, we want I to stop 1 before the end, and we want J to stop on the end. That's the difference. All right, so now here, if, remember K will be the smallest value that we've seen. Now I see where K has to be. I don't know if I can ask this. Let me see. I'll leave it as a question there. We'll need to initialize K to something. And when we have, remember on this inner loop, think about this. This is the outer loop, this is the inner loop. Now, at each point in the inner loop, we'll have 2 values. We'll have an I and we're going to have a J. And the main purpose of that inner loop is for J to range across the values to the right of I. So we're going to look at V of J. Now what is it we're going to do with V of J? We're going to compare it to, the value at K, exactly. So if V of J is smaller than V of K, we're asking the question, are we at a smaller value than the smallest value we've seen so far? If we are, then what do we do? Huh? Anybody back there? What do we do? I know you know the answer. Anybody know what to do there? We have to update K. They say, wait a minute, we just found J, a new smallest value. So let's update K to point to the new smallest value. Remember, K is going to point to the smallest value that we've seen so far. So let K point to the smallest value we've seen so far. Scan the values to the right of I. Searching for the smallest value. I don't really like that. Maybe that's all right. I don't know if those comments help. Does this comment help?
Yeah.
To me, it makes it harder to read the code. So I'm going to take it out. But I'm going to leave this one in. This sort of sets the meaning of what k is. Let k point to the smallest value we've seen so far. So what do we initialize k to? Here we're starting the loop. Remember, here we're in this loop. We've just incremented I. We've just advanced I to a new position. And we're going to let j start at I plus 1. So what do we set k to as a starting point? Well, anybody see that?
It's a question mark.
It's not a question mark.
Wouldn't it be I?
I. Good job. I waited for one person to get it. I know there's a lot of people here. One
Good
person
guess,
gets
man.
it.
Good guess. Good guess. Good guess. Oh.
It was either I or J, you know. I mean, yeah, see, the smallest value that we've seen up to this point is the value that we're at, I. So we're looking for a value that's smaller than the value at I. So we're going to start with the value at I being the smallest. But no, you know what? We could do it. We could do this. We could do it. There's many ways of doing this. We could do it like this, actually. We could set it to the place where J is. But then we would have to do another comparison later on. It's another place to start. But I'm going to start here. I think this makes a simpler solution. This cuts down on one comparison that we need to do. Maybe. Actually, maybe it doesn't cut down. All right, what else do we do? Well, I'll give you a hint here. We've got to do something here.
Return?
No. We are not going to return until we're down here. We have to let I scan from 0 to v dot size minus 2. And of course, that return is implied. We're at the bottom of the function, so we don't need to include that. We're in a void function. We can omit the return statement there. So what do we need to do? What have we accomplished? When we finish the inner for loop, what have we accomplished? We've determined k, right? But now that we have k set to the smallest value, starting at I and going to the end of the vector, what do we do with that information?
Swap I and K.
Huh?
Swap I and K.
Got it. Swap the values at I and k, exactly. Swap the values at I and k. Now the values from 0 to I are all the smallest values in the vector, and they're in sorted order. So we're going to keep moving I to the right now. Now, I want to show people how to swap two values in case you ever need to do that. Because swap is defined. I believe that works. And just to show you, in case you weren't aware of swapping, of that swap function, I'll show you how to swap two values. You have to have a third variable. So let's call that variable, say, temp. Set it to v of I. Now we can modify, now that we've preserved v of I, we can modify v of I by setting it to v of j. Now that we've used v of j, we can set it to what we need to set it to, which is the value stored in temp. That's how you swap two values. Okay. But there is a swap function, so we don't have to do that. At least I think there's a swap function. Okay. Is there anything else we need to do? That's it, right? All tests passed. Look at that. That's it. That's not a lot of lines of code. I'm going to take this out to make it more readable. We left one comment in there. So this is one way to do it. I'll show you another way to do it. I'll just rename that. So let's do it without using this variable k. How can we do it without using k? Anybody want to try that? Actually, don't even need this. Here, we are comparing the value at j with the value at I. So remember, j is scanning across to the right of I. And if we find a new value j that's smaller than what's at I, then we'll swap those two values. Look at that. That's a lot smaller, isn't it? But we potentially call swap a lot. And I showed you swap does, those three copy operations. So this is maybe a little bit slower, but it probably wouldn't notice it unless we had. We wouldn't be sorting using this routine anyway. To tell you the truth, I think readability is more important here. And doesn't this look more readable? See, we start wherever I is. We're going to find what I'm going to scan to my right, and whenever I find something smaller than what's at I, I'm going to swap it with I, and I'm going to eventually get the smallest value in slot I. And then I advance I, and do the same process all over again. Which one of these are you going to memorize for the exam? And there's many more ways of doing it than this way. And I also I'll point out later in this lecture that in fact these are all inefficient sorting routines, and that there are faster routines.
So why are we learning these?
Because the efficient routines are too complicated to understand right now. But these routines are faster for smaller vectors. So what the very fast routines that are used in practice, if the vector size is small, like I think it's 10 items or maybe 40 items, I don't know what the number is, that they'll use they'll use this type of sorting routine rather than the faster faster routine. I'm trying to remember the names. There's merge sort, and there's was it the pivot sort? I can't remember. Quick sort, that's what they call it. Quick sort. I think that mostly people use quick sort. There's this thing called quick sort, but it uses quick sort relies on recursion and just a more. I guess we could cover it actually if you wanted to. It's not normally covered in this quarter. Does the book cover quick sort or merge sort? It does merge sort? The book covers merge sort? We could look at that. Yeah. Do you want to see if this works?
Sure.
Right. There we go. So you should be able to come up with this on your own, like in an exam. This would be a kind of a question you might get in a job interview. You might sit down and say, oh, just write some code. It doesn't have to be an efficient sort. Just write down some code that does that sorts a list of values. And then you would come up with something like this in a job interview. So you don't want to just memorize this. You want to practice kind of coming up with it. And there are other ways of sorting. There's like this bubble sort or selection sort, insertion sort. So all kinds of variations. And I've shown you two right here, but there's even more. So you could try coming up with a different approach and then testing it using test code, just the way I've shown you here. And you really want to do that. If you want to become a programmer, that is, if you're not interested in doing that as work, then you don't need to practice developing algorithms. But at this point, for those who do want to do programming later on, you need to practice developing algorithms. And this is a good type of algorithm to work on. Now try to do it on your own. Try to go through the reasoning on your own and coming up with this sort routine on your own. And spend some hours doing this. Don't expect to get it in 15 minutes. Spend a half a day on this. All right, now I want to show another thing here. Let's see what else is in here. Oh, comparison. Oh. Let's look at the second exercise. Create two programs defined in slow.cpp and fast.cpp. In slow.cpp, generate a random vector of size 100,000 and pass it to your sorting algorithm. Run the program and observe that it never ends. Press Control-C to terminate the process. In fast.cpp, generate a random vector of size 100,000, the same vector, and pass it to the sort routine that is part of the C++ standard library. So that would be a sort routine, probably quick sort. That is an efficient sorting routine. We'll see how much faster it runs. All right, let's do this. All right. So we've already tested this routine. Oh, that's this one. I wanted to use the, that's all right, we'll use this one. This is our more efficient implementation. So we've already tested this code. We know that it works. So we're going to just see how well it works on a large vector. So we're not actually running a test. I'm just going to say done. I'll spell that right. So let's create the vector. and it was 100,000. And let's call pushback on the vector. And we'll generate a random value, random integer. When we create the vector, so just to save some effort, we'll tell the system how big to make the vector. So when we call pushback, it doesn't have to reallocate memory. It allocates enough memory to hold 100,000 values. And then we call sort. Let's see what happens.
Wasn't it? Couldn't go through it, so you're not gonna really see it because it tells you you have to Command C out of it because how long it takes.
I think it should finish in under a minute. Well, it takes some time. Let's just let it run, okay? And we're going to copy to, let's create the fast one. So we need to use the header file, I think it was algorithm. Let's check it. Is it done yet? Not yet. So here's the fast one. The fast one, we're basically going to call the sort routine,
Bless you.
like that. All right. Did that finish yet? Not yet. So let's compile the fast one. And oh yeah, I know the sort. It has to be like this. 0 to no, wait a minute. V dot front. Yeah, V dot end. Thank you.
Or is it V dot? Because I was doing it and I had to do the V dot begin to V dot end.
Oh yeah, begin. Thank you. Thank you very much. Good. Oh, it's done. So that finished. That finished. One error. What is going on?
I
You
thought
get
it was
the
V dot sort,
Oh, it's V dot sort.
V dot sort, and then it's just V dot begin to V dot end.
So it's a
I think you can.
it's a function
Yeah,
within V.
I'm pretty sure.
Did I forget to save?
don't you have to include the algorithm library?
I
Already
did right there. Oh, I was saving the wrong one. Was it the problem? Oh, I went in the wrong file. Sorry. It's v dot sort. I was in the wrong
And
file.
then V dot begin, V dot end.
There we go. All right. I was in the wrong file.
It's just sort.
Just so I had it right the first time.
You have to include the algorithm.
That's it right there. That's it. I think that's it. Ah,
Oh, you didn't save it.
no. Oh, I included it in the wrong. No, I did. I got it right there.
Right, you didn't even get rid of
Take off the V's now.
the, yeah.
Oh, the V.
right
Oh, I
there.
didn't see that. I'm getting lost. Which file I'm in, right? That worked. Ay, ay, ay. All right. Ready? Look at the difference. Can you believe that? Not even enough time to wink, you know, to blink. That's an amazing difference. So there's kind of the moral of the story here is that it's important on how you design your algorithm so that it runs efficiently. Now the code that we have done here. So let me look at the other one. It's easier to look at. Right here. You see there's two loops, one inside of another. As if you think about how many times, the problem is the way to analyze this algorithm is to look at this operation that's in the innermost loop. How many times does this thing run? And we can actually calculate the number of times that thing runs. If you look at the outer loop, I ranges from, let's suppose that n is the size of the vector. And then the outer loop runs n minus 1 times. Okay? The first time the outer loop runs, the inner loop runs n minus 2 times. Because j starts at 0 plus 1, which is 1, and it stops at v dot size. So it runs this code n minus 1 times. So the first time the outer loop runs, the inner loop executes this comparison n minus 1 times. It doesn't always do the swap, but it executes the comparison n minus 1 times. Now then, I is incremented from 0 to 1. And now j starts not at 1, but at 2. So that loop now runs, that comparison right here is executed n minus 2 times. And so on. You know, until we get down to like this. So in math, there's an equation for this. It's, what is it, n times n plus 1 divided by 2. Did I get that right? Of course, that's if you start at n, right? So you have to subtract n from this. So we're starting at n minus 1, so this would actually be n minus 1. To be precise, this would be n minus 1 times, I'm sorry, this is n minus 1 times n. And this thing equals, 0.5 times n squared minus 0.5 times n. And if you make n large, then this term, a half times n, is unimportant. And the squared term dominates. So the number of times the comparison executes is proportional to the square of the number of values in the list. So as the number of values grows, then the amount of time it takes to run the algorithm blows up. Because if you look at a graph of n squared, you know that it starts to increase very rapidly. So we call this algorithm it has what's called quadratic running time. The time that it takes for this algorithm to complete is proportional to the square of the items in the data. And there's a notation called the big O notation. So we say that the algorithm runs in n squared time. So that basically we denote it like this. We saw how much faster that the built-in sort routine runs. And that time complexity is n times log n. So with some way to cleverly design the algorithm, we can make the time to completion proportional to n times log n rather than n squared. And that difference, and we just saw experimentally how important, how significant that difference is. Now, log n is not very big. It's bigger than a constant. It'd be nice if the running time were proportional to n. Like linear search. When you do linear search, we've done linear search. We looked at that. Linear search has this time complexity. In other words, the time it takes to perform a linear search is proportional to the number of items in the list. Here, the time complexity to sort n items is worse than linear search, but only a little worse, only by a factor of log n. So it's a reasonable sort of solution. It's not too hard to sort many values. Now, if you have binary search, it's even faster than linear time. Binary search completes in an amount of time that's proportional to log n. And because in binary search, you have n values and you keep chopping it in half. So at most, you're going to do n chops to get to the smallest sort of interval inside your search. So this is super fast. Of course, even faster than this is algorithms that run in what's called constant time. It doesn't matter how many values you have, the algorithm is going to complete in a constant amount of time. Now, sometimes, when you're analyzing code, you say, "Oh, that's an O1 operation," so that's nothing. And so when you analyze code, especially when you take the course on data structures, which is coming up in 2 quarters for some of you, that you'll be analyzing algorithms that you develop using this notation. So the book covers something called merge sort, I believe, right? So I don't know if we're going to look at that or not. I mean, maybe we will. I think what I'm going to do is look more at the tic-tac-toe problem and talk about that towards the end of the class. It has more to do with software engineering, like testing and what's a strategy that you use to code a problem. That's an area that I'm more interested in, software engineering. So this area here called algorithm analysis. This is a topic that is covered in more depth in later courses in our programs here. Yeah, question. Well, that's not just Nathan that's sleeping, it's a whole bunch of people.
Oh, really? I just want to have like a moment where you start clapping and everybody starts clapping. You just see him wake up like this.
Well, anyway, I think that's enough for today, isn't it? I'm trying to think if I forgot to mention anything. I think that's it. All right, that's it.